specific shape. They do not have linear and aerial expansion as solids do. They have expansion in volume only. When a liquid in a container is heated, both the liquid and the container expand. Hence, for liquids, we have two categories of expansions, namely real and apparent. The apparent expansion of a liquid is the expansion that appears. The apparent expansion of the liquid is equal to the real expansion of the liquid minus expansion of the container. Unlike other liquids, water exhibits irregular expansion between 0 degrees centigrade and 4 degrees centigrade. If the temperature of water is raised from 0 degrees centigrade to 4 degrees centigrade, instead of expanding, it actually contracts. This means a given mass of water occupies least volume and, as a consequence, will have maximum density at 4 degrees centigrade. This anomalous expansion of water enables aquatic animals and plants to survive in water. Lakes and ponds freeze first on the upper surface of water. The frozen water body, which is the ice, floats on the denser water. When a solid, liquid and a gas are heated, the gas expands more than the solid and the liquid. For ideal gas, PV is equal to mu RT. Let this be equation 1. If the pressure of the gas is constant, on differentiating equation 1, we get P delta V equals to mu R delta T. Let this be equation 2. On dividing equation 2 by equation 1, we get delta V by V is equal to delta T by T. But delta V by V is equal to alpha V into delta T. Hence, for an ideal gas, alpha V is equal to 1 by T. For gases, the coefficient of volume expansion is inversely proportional to the absolute temperature of the gas. Let us now discuss thermal stress. Consider a rod rigidly fixed at both ends to prevent expansion. If the temperature of the rod is changed, then the stress that develops in the rod is called thermal stress. The stress developed in a body when not allowing it to expand while heating is called thermal stress. If the length of the rod is L and delta L is the change in its length for a temperature change of delta T, then delta L by L is equal to alpha L into delta T. Let this be equation 3. If the rod is rigidly fixed, then thermal stress is expressed as F by A, which is equal to Y into delta L by L, where Y is Young's modulus of the material. Let this be equation 4. From equations 3 and 4, thermal stress is expressed as Y into alpha L into delta T. The force F acting on the rod must be equal to the product of Y, A, alpha L and delta T.